Howdy, today on Flippin Science we're looking at ocean acidification. So science understands we're going to look at ocean acidification is caused by the ocean absorbing higher levels of carbon dioxide from the atmosphere. So describe and write equations showing how carbon dioxide lowers pH. Then the skeletons and shells of many marine organisms are made of calcium carbonate and are vulnerable to low pHs, so write equations for carbonates reacting with acids. So let's talk about carbon dioxide. Carbon dioxide is an acidic oxide. One of the properties of acidic oxides is if they dissolve in water they produce an acid, and in this case it's carbonic acid. And here's an equation here, but we'll go through the equations in a minute. Where does the carbon dioxide come from? It's from the combustion of carbon-containing compounds, so things like coal and petrol. When you burn them in oxygen they produce carbon dioxide. So down here we have octane, which is a component of petrol. You burn that on oxygen, you produce carbon dioxide molecules. Those carbon dioxide molecules can then dissolve in the ocean, and we're going to look at the effects that has. We know the levels of carbon dioxide in the atmosphere have increased significantly over recent times, and we're seeing that effect on the oceans. Here's what's known as the Keeling curve. It's a measurement of carbon dioxide on a volcano in Hawaii. It's been done since about the 1960s. It goes up and down. It goes down in the northern hemisphere's summer because there's more light hitting the northern hemisphere and there's more trees in the northern hemisphere, so you get more photosynthesis happening. And it goes back up in the southern hemisphere's summer. There are less trees in the southern hemisphere, so we don't get as much carbon dioxide being absorbed. But the overall trend you can see is upwards over the last 40 years or so. If we have a look over a longer period, and we can measure the carbon dioxide that's been produced over the last 10,000 years by looking at ice cores. So little bubbles of air get trapped in ice, in snow as it falls, and that gets compacted into ice, and you can measure from the little bubbles of air left over how much carbon dioxide was in the air. So going back 10,000 years, we can see there is a gradual increase until we hit the 20th century, and then it just goes really, really up. Here, this is a little bit out of date, this one. We're well over 400 parts per million on average a day now. So this is the 400 parts per million line, we're over that. So carbon dioxide dissolves in the ocean to produce an acid, carbonic acid. And carbonic acid is a reasonably weak acid, but in solution it dissociates and produces two hydrogen ions. Those hydrogen ions then react with water to produce hydronium ions, and hydronium ion concentration is related to pH. The higher the concentration of hydronium ions, the lower the pH. And we're going to have a look at the effect of pH shortly. What this means is that the ocean is becoming more acidic and the pH is lowering. So let's do some equations showing how carbon dioxide makes the ocean acidic. So first thing is carbon dioxide dissolves in water to produce carbonic acid. Carbonic acid is H2CO3. Okay, so this is in solution, aqueous, that's a liquid, and this is a gas. Now there's properties of gases dissolving in liquids that we'll look at a bit later on. Now the carbonic acid, the H2CO3, that will dissociate in water to produce a hydrogen ion and a hydrogen carbonate ion. And then the hydrogen carbonate ion will dissociate as well, and that will produce another hydrogen ion and a carbonate ion. So we get this from here, we get another breakdown. So we're getting two hydrogen ions being produced. And whenever you have a hydrogen ion being produced in water, you produce a hydronium ion, H2O, and that goes to H3O+. So another way of writing what happens is the carbonic acid, so H2CO3 plus two water molecules goes to carbonate ions, CO3 2-, plus two hydronium ions, H3O+. And this is what's responsible for lowering the pH of water. There's a few equations we can do here showing the same thing going on, but the key is that hydrogen ions are being produced. Those hydrogen ions are then dissolving in water, reacting with water to produce hydronium ions, and that lowers the pH. So let's have a look at this effect. So historically, here's the Keeling curve that we had before. So atmospheric carbon dioxide concentration going up. Next to that we have some seawater that's in the same area of Hawaii being measured. They're measuring the amount of carbon dioxide in the water, I believe, so that's going up as well. And they're measuring the pH. We can see over time the pH is decreasing down here. Now, it's not a huge level. We're going from 8.1 down to 8.08, but that's still over a large ocean, that's a huge effect. That's a huge amount of acid going into the ocean. And again, we can go back in time by looking at rocks and seeing what's happened to the pH over time as well. So in this case, rather than going thousands of years, we're going millions of years back in time. So you can see there is some variation over time, going back 24 million years ago or so. But as we get to today, we can see there's a huge drop. And again, on average, the change from 1800 to now, well, this is predicting in the future. So we've seen this drop here, as that's from the 8.2-ish down to the 8 points, well, just below 8.1-ish. So that's what's happened in the last 200 years, and then using mathematical models, they've predicted what's going to happen over the next 100 years. That's going to see an even starker drop in pH. So why isn't this good? Anything with a calcium carbonate shell in the ocean will be affected by a drop in pH. And anything that eats anything that has a shell will also be affected. So whole huge swathes of the ocean can be affected by this. Calcium carbonate reacts with acid to produce carbon dioxide and water. And we use this as a bit of a test in Year 8 to show you how to test for carbon dioxide using lime water. So let's have a look at some of the effects. So here we have a sea urchin, which is an echinoderm related to a sea star. We see under normal carbon dioxide, it's got lots and lots of nice big spines coming off of it. Under higher concentrations of carbon dioxide dissolved in water, so the water is slightly acidic, we can see those spines aren't forming anymore. Here we have an experiment that was done with, again, these are microscopic shells, these are very small shelled organisms. So at 0 days, then they put it in an acid solution of acid, approximating that's what's going into the ocean now. And what's happening is the shell is dissolving, so over time the shell dissolves. Here we see a similar experiment, again on microscopic shells that you can't see. Down here we have a coral reef that's having a few effects on it. One thing is that the concentration of carbon dioxide is increasing, that's the parts per million here. The other thing is the temperature is increasing. As these are going hand in hand, they're having huge effects on the reef. Last one we'll have a look at, here's a pteropod, so this is again another small shelled creature, so the organism lives inside the shell. This is kind of regular carbon dioxide, and this is under higher carbon dioxide conditions. The shell is weaker. The organism was having troubles swimming around because of the structural defects in the shell. So, acidification of the oceans isn't good for living things in the ocean. As I was saying, many marine creatures have shells and skeletons made of calcium carbonate. And fundamental rule that you would have learnt in acids and bases, metal carbonates react in acid to produce a salt, carbon dioxide and water. So let's write some equations showing that. We're going to use hydrochloric acid here rather than carbonic acid, which is present in the ocean. The reason for that is the interaction between carbonic acid and what's going on in the ocean with calcium carbonate is a little bit complicated. But we're just going to use hydrochloric acid as a bit of a proxy. So calcium carbonate, CaCO3, is reacting with hydrochloric acid, so salt plus water. Salt is the negative part of the acid and the positive part of the base. So in that case, this is the metal carbonate. So that's calcium. Now, calcium has a 2+ charge. Chloride has a -1 charge, so we're going to need 2 of those to balance it out. Plus carbon dioxide plus water. And to balance that, we've got 2 hydrogens here, only 1 hydrogen here, so we need 2 of these. So we should have 1 calcium, 1 calcium. 1 carbon, 1 carbon, 1, 2, 3 oxygens, 1, 2, 3 oxygens, 2 hydrogens, and 2 chlorines. So now we're balanced. Now we could write an ionic equation showing what's going on just using the hydrogen ions from the hydrochloric acid and just using the carbonate ions from the calcium carbonate. So the carbonate ions, CO3 2-, we're reacting that with 2 hydrogen ions that we're getting from the hydrochloric acid. And again, that just goes to carbon dioxide plus water. And that should be balanced. We've got 3 oxygens, 1, 2, 3 oxygens, 1 carbon, 1 carbon, 2 hydrogens, 2 hydrogens. So this is an ionic equation. We get rid of the spectator ions, the calcium ions, the chloride ions that would make the salt. So in both of these equations, though, we get something solid turning into, in this case it's a salt, but this would dissolve in water, and it produces a gas, carbon dioxide and water. So if your shell is made out of the calcium carbonate, it will dissolve in the water to produce something soluble. And that's the case for carbonic acid as it would be for hydrochloric acid. So here's some questions. Solubility of carbon dioxide and water varies with temperature, as shown in the graph below. State the effect the increase in temperature has on the solubility. So if we have a look at the temperature, as the temperature increases, the solubility is decreasing. So that's the effect. So the solubility decreases as the temperature increases. And this is true. As you heat up water, the gas comes out of the water and goes back into the atmosphere. Using the graph above, explain the effect that increasing temperature has on the pH. Now, so as we're increasing the temperature, you would expect the pH to, now we're getting less carbon dioxide dissolved in the water. So if there's less carbon dioxide, it's less acidic, so the pH is going to increase. So as the temperature increases, the level of carbon dioxide will decrease, so the level of carbonic acid will also decrease, so the pH will increase because there's less hydronium ions in there. The question continues. So despite the low solubility of carbon dioxide, oceans may have absorbed more than half of the carbon dioxide generated by human activity. This increased level of carbon dioxide in the oceans has been accompanied by a relatively constant average ocean temperature. So even though the temperature of the ocean is increasing, the amount of carbon dioxide increasing in the ocean isn't matched by the increase in temperature. So although this graph is true, due to the small change in temperature, the pH effect is greater. Okay, anyway, calcium carbonate in the shells of many more organisms reacts with hydrogen ions. Write an equation for the reaction of calcium carbonate with hydrogen ions. Okay, so this is slightly different to what we had before, but we'll have our calcium carbonate. We're reacting it with hydrogen ions. And we need to think of what we're going to be producing. So we don't have our negative part of the acid, so we're just going to be looking at the positive part of the base. So in this case it's calcium ions we're producing, and metal carbonate plus acid goes to salt plus carbon dioxide plus water. So let's put in our carbon dioxide and let's put in our water. Now we need to balance this. We've got two hydrogens over here but only one over here. So we've got two H pluses. So we're just using hydrogen ions here. So calcium carbonate plus hydrogen ions goes to calcium ions. So that's the positive part of the base, plus carbon dioxide plus water. One calcium, three oxygens, one carbon, two hydrogens, two hydrogens. So we're balanced. The charge is also balanced. We've got 2 plus in total on this side and 2 plus in total on this side. State the effect of this reaction on the shells of marine organisms. The shells of marine organisms will dissolve in the water. They will get thinner. They will become weaker as they become thinner. So there's many effects that you could talk about, but really the solid calcium carbonate in the shell will dissolve into a soluble salt in the solution. So today on Flipping Science we looked at ocean acidification. That's it for Flipping Science today. See ya.